Hello everyone. Today I would like to go through a mathematical induction question. Mathematical induction is one of the topics in further maths, and while the concept may seem easy when you learn it for the first time, when you actually do questions, you may realize that it's not as easy as you think. One of the common ways to test mathematical induction is differentiation, and this is exactly what is done in this here. This is ACJC Further Maths Prelim 2018 Paper 1 Question 5. So let's go through this together. For the first part, we must show that the derivative of inverse cotangent x is negative 1 over 1 plus x squared. So I'm going to let theta equals to cotangent inverse of x. And of course, this implies that cotangent of theta is equal to just x. Now we differentiate implicitly with respect to x, we get negative cosecant square theta d theta dx is equal to 1. And now d theta dx is equal to 1 over negative 1 over cosecant square theta equal to negative 1 over 1 plus cotangent square theta by trigo identity. And since cotangent of cotangent inverse is just whatever is there, we have negative 1 over 1 plus x squared. And this is shown. Alright. Yeah, just need to do implicit differentiation and trigo identity, and this part is fine. For the second part, we need to show that sine of cotangent inverse of x is 1 over 1 square root of 1 plus x squared, and find the similar expression for cosine of cotangent inverse of x. So for this, you just draw your triangle like you did for O levels every time you did this kind of question. This will be theta. This is a right angle, and then we can let this be 1x square root of 1 plus x squared. And then from the diagram, we can just see that sine theta, which is sine of cotangent inverse of x, is equal to just 1 over square root 1 plus x squared, because we can see that this is the opposite over the hypotenuse, and adjacent over hypotenuse gives us cosine theta, which is just x over the square root of 1 plus x squared. So this part is also quite simple. Now we have to show that for all positive values of x, this is true. That is 1 over square root 1 plus x squared, whole thing multiplied by cosine of k cotangent inverse of x plus x times sine of k cotangent inverse of x. Whole thing of this is equal to sine of k plus 1 cotangent inverse of x. So 1 over square root 1 plus x squared is just sine theta, right? So sine theta cosine k theta, and then we have plus, now x over square root 1 plus x squared is cosine theta, so I can write this as cosine theta and sine k theta. And you might realize that this is just addition formula for sine, so we will get sine of theta plus k theta, and of course we can factor out the theta, and we will get theta times k plus 1, but theta is cotangent inverse of x, so this is equal to sine of k plus 1 cotangent inverse of x, and this is shown. Alright, so now that we have done this, we can reach the climax, the actual proving by induction. So we have to prove by induction that the nth derivative of tangent inverse of x is negative 1 raised to the power of n minus 1 times n minus 1 factorial all over 1 plus x squared whole thing raised to the power of n over 2. Then this entire thing multiplied by sine of n cotangent inverse of x for all positive integers n. So we do the standard, let Pn denote the statement. I'm too lazy, so I'm gonna just asterisk this. Okay, is true for all n in the positive integers, right? Okay, so we will check P1 to start, because that's the smallest positive integer. So we have d dx of tangent inverse of x, and this will be equal to, based on the formula, give me 1 minute, Alright, based on the formula, this is supposed to be negative 1 to the power of 0 times 1 minus 1 factorial all over 1 plus x squared to the power of half, and this whole thing is multiplied by sine of cotangent inverse of x. And now the top is just 1 over square root of 1 plus x squared, and this side here, and we have just proven that this is 1 over square root of 1 plus x squared, and this is 1 over 1 plus x squared. And this is true because if you don't remember this is actually just the derivative of tangent inverse of x. It is in your MF26 if you do not remember. So this is true. P1 is true. Now we do the induction step. Assume that it is true. Assume that pk is true for some positive integer k. So alright, now we will try to prove that p of k plus 1 is true, right? Okay. So we are just asking ourselves if this is true. So we need to find the kth derivative, or sorry, k plus 1 derivative. So dk plus 1 over dx k plus 1 of tangent inverse of x. And of course, this is just the derivative of whatever the expression is. So this is, now first of all, the top is a constant. This negative 1, k minus 1, then k minus 1 factorial. This whole thing is actually just a constant. I'm going to put it outside. And then in the inside, I'll write this as a quotient. Sine of k cotangent inverse of x. And then divide this whole thing by 1 plus x squared. And this is raised to k over 2, right? Okay. So we need to take this derivative and then somehow get back to this being true. So this would be equals to, let me just write down the constant again. Okay, and then we will do our quotient rule. So this is going to be a very big thing, but this is going to be 1 plus x squared to the k over 2. Then the derivative of the top is going to be, we're not going to simplify it in terms of k because we can just do the implicit differentiation, and we should get, I believe, negative k over 1 plus x squared, and then this is multiplied by cosine of k cotangent inverse of x, and then we subtract sine of k cotangent inverse of x, and I don't think I have enough space for this. We need to differentiate the bottom now. Oh my god, this pen is not very good. Alright. And now we differentiate 1 plus x squared holding raised to the power of k over 2, and we will get k over 2 times 1 plus x squared k over 2 minus 1, and then the derivative of the inside is 2x, so chain rule, and this whole thing is divided by 1 plus x squared to the power of k, because we must square the denominator when we do quotient rule. Alright, yeah, maybe I'll zoom out a bit. Okay, and now this is equal to the outside constant again. There's a lot of things to take in though, so let's simplify. Let's actually simplify before I do anything else. So let's have a look here, if we can. Alright, I can see that this and that will cancel. And later on, I can factor out k, because then this, and this will all cancel. And if I multiply out the negative, because there's a negative here and a negative here, so both sides are negative, meaning that I can rewrite this as negative 1 over, to the power of k and k factorial. And now I can start to simplify stuff. So this is 1 plus x squared to the power of k over 2 minus 1, and then cosine of k cotangent inverse of x, then plus sine k cotangent inverse of x. Then we have one plus x squared, k over 2 minus 1, then multiply whole thing by x, and then this whole thing is divided by 1 plus x squared to the power of k. Alright, and notice that now we notice that this and this are common, and we also notice that we have this and this. Now this green one is very important, because if we come back up to the top, we actually found this earlier, right? We have proven this. There's a reason why they ask you to prove that, because now we can simplify something. So if I bring this over to the right side, which we can, alright, and then we'll just clean things up at the same time. So this is equal to negative 1 to the power of k times k factorial, and we can expand this. So we have 1 plus x squared to the power of k over 2 minus 1, and then we group everything together. We have square root of 1 plus x squared times sine of k plus 1 cotangent inverse of x, and this whole thing divided by 1 plus x squared to the power of k, and right, we can write this as negative 1 k factorial, and let's evaluate the power. So this is going to be k over 2 minus half, and then we minus 1, so this becomes minus, so this whole thing becomes minus k over 2 minus half, which means that it goes in the denominator, and it will become 1 plus x squared, the negative will be gone, and this becomes k plus 1 over 2, and this multiplies by sine of k plus 1 cotangent inverse of x. And that, folks, we are done, I believe, because if we look down here and we go back up, we see that our final answer is exactly of that form, except that we have changed n, we have replaced n with k plus 1. So therefore, if we assume that p of k is true, that it implies that p of k plus 1 is true. So we have done everything we needed to prove by mathematical induction. So therefore, by mathematical induction, we can write the statement p n is true for all positive integers n, right? So let's write that. And yeah, that is an example of mathematical induction. Um, not an example that is incredibly easy. There may be even harder examples, but this is just one example. So not only do you need to understand how this proof works, but you also need to understand a lot of algebra to be able to pull it off well. That's it from me for now. I hope to see you guys real soon, and maybe we'll go through more induction questions if there's requests. Um, I'll have to see how I am doing with the rest of my JC topics. So I'll catch you all real soon.